we were discussing second order linear systems in phase space, and then I was telling you something about fixed points and why they're more interesting in 2D systems. And we were talking about the general 2D linear system. I think we started discussing the case when you had a coupled set of first order ODEs like this. And then we noticed that you can take any linear second order ODE and put it into this form. Autonomous, of course, we are talking only about autonomous systems. So remember, we did the analogous thing for the 1D case, and then I told you in the last session that you could take a non-autonomous 1D system and then change t, make a dummy variable and make it a 2D system like this. And presumably you can do the same thing over here. y1, y2 are both functions of t. If you had some explicit t dependence here, even though the equation is linear, if you had an explicit t dependence, you could introduce another dummy variable y3 and then have dy3 by dt equals 1, and then you'll have a third order system. You'll have a 3D or 3 simultaneous linear system. So things change a little bit, but okay, we know how to handle it presumably. Okay, and then telling you that this matrix A plays a central role, and then we looked at two examples. One was when you had complete decoupling. So I had, I think, example that looked like this, and then the other when you had complete coupling. I think it looked like this: d2 minus q naught and 0, something like this. So one case it's perfectly diagonal, the other case it's perfectly off diagonal, and we looked at what the solutions were like. Right? This one we could solve. Completely decoupled first order linear ODEs are solvable. You had y1 was like exponential of alpha t with some constant. I'm not going to bother about the constants for now. And y2 was like e to the power of minus t and so on. And then we said that one decays, the other one either decays or grows or whatever, depending on what value alpha is. If alpha is negative, both will decay, and eventually all the trajectories will come towards the origin, and so the origin was stable fixed point. Okay, so if you remember, again going back, for alpha negative, origin, oh, and of course the origin was the only fixed point here, right? So we found fixed point for which these equations must simultaneously be equal to 0 on the left hand side, because by definition of a fixed point you start there, you stay there, so there are no derivatives at that point. And so the origin is the only fixed point if you have a linear system like this, and then okay, you know, it's that particular fixed point is completely absolutely stable. Absolutely stable. Again, now we'll see that we did see distinction between Lyapunov stable and absolutely stable. We'll emphasize that a little bit again today. And depending on the value of alpha, alpha negative completely stable, alpha positive we had a saddle, and again we emphasize the fact that you cannot have a saddle in a linear 1D system, 1D alone linear system, because if you wanted to have a saddle, the function right hand side f of y had to come and do a u or a v type of thing, and the v will be non-differentiable at that fixed point, so that's not possible. And so that was the case for this when you had a diagonal matrix for A. Now on the other hand, if you have a, when we looked at this situation, we could go back and solve the original equation. It was just d square y by dt square plus q0 y equals 0. We can solve this. If q0 is taken to be positive, you will get a solution that has sine of square root of q0 t times constant 1, right? I'm going to write that down. So you will get y1, if you change again, dy by dt is y2 and y is y1. You can put this into this form like here with this matrix, and then you will get some constant times sine of square root of q naught times t, and the other one will be cosine with some constant, of course, which I'm going to drop for now. Okay. So if you do this, then we saw that for this solution y1 and y2 cosine omega t sine omega t, they are basically going to give you an ellipse. Depending on what this constant is, you will get the equation of the ellipses. If this was a and this was b, this will be y1 by a the whole square plus y2 by b the whole square must be equal to 1. So if you go back to phase space, we had y1 and y2 like this, and the first guy, this guy, all the trajectories, if alpha was negative, all the trajectories came like this, otherwise you had a saddle, stuff was going away like this, right? The second guy will give you closed ellipses like this, with this at the center. Okay, this guy. Now this trajectory is Lyapunov stable because again I mentioned this briefly. If you start close enough, if this is, let's say, epsilon, remember what Lyapunov stability was, again going back to the definition. If I have norm of y minus or y naught minus y star less than delta or epsilon, then if for all t norm of y of t minus y star is less than epsilon, then this y star is Lyapunov stable. Epsilon delta very small number. So if you start, now you have to have y0. So y0 is now a vector, right? These are all vectors now. So y0 bar is the starting point, y10, y20, starting point of the trajectory. It has two coordinates. And likewise, y bar of t is likewise given like this, y1 of t, y2 of t. And this norm is just square root of y1 square plus y2 square, right? The usual L2 norm that you use for vectors in space. So if this happens, then it's Lyapunov stable. Of course, if we let's say start at a point here, this is delta, the maximum value that this guy is going to take is presumably going to be this. Okay, if this is the major axis, that's the minor axis, then this is the maximum value. But it's of the order of epsilon or delta, right? It's a small trajectory, it will keep going around. So this point is Lyapunov stable because the trajectory remains in the vicinity of y star. The origin now, the fixed point at the origin is Lyapunov stable, but not absolutely stable because it will never reach. Even you take t goes to infinity, it will still be going around, right? It will never reach the point. So it's not absolutely stable. So that's a example we saw of something that is Lyapunov stable but not absolutely stable. So what I'm going to do today is I will talk about slightly different situation, and we'll try to generalize this. So what we want to start first, okay, before we go to the different situation of nonlinear systems, is we want to, remember this is all linear, we want to be able to ask the question, given a fixed point at origin, so you just take a linear system, so 2D linear. The question we want to ask is, look at the matrix A for that system that I wrote down before, which I just got rid of. Look at the matrix A, and from here can we predict the behavior? Okay, that's the next question we want to ask. Can we look at this matrix and then say something about, is the fixed point going to be stable, unstable, whatever? Okay, and this is the analog of what we did for the 1D case. We had dy by dt is equal to f of y. We could say if df by dy at the origin, it's a linear system, was positive, negative, we could say it is a fixed point, a stable fixed point, unstable fixed point. Now we have more possibilities. Remember, we said that you can have these rotating closed trajectories in 2D, not only the stable points but also unstable points, saddles, closed trajectories. I also mentioned that you can have spirals, stable spirals, unstable spirals, and so on, which will happen if you had a system that had, let's say, A equals 0, but you had B positive, C and D, like you have a damped oscillator, it will eventually go to 0, damped spring mass system. So there are way more possibilities. So we want to see if we can look at the matrix A, compute some of its properties, and then say something about some of these, which of these should appear, right, as a function of these properties. If you're given a matrix A, the first thing you will do is diagonalize it. and that will give you the eigenvalues, and from the eigenvalues you can get the eigenvectors. So presumably, like I said at the end of the last session, all this information is encoded here, and the eigenvalues and eigenvectors, and so that's what we'll compute. Okay, so we'll take this matrix and compute all of these properties, and then depending on the eigenvalues, eigenvectors, we'll reinterpret the behavior of the system in the context of the original 2D system. Okay. Okay, in the original context. So right now all we're going to do is matrix algebra. Simple matrix. I mean, this is the simplest matrix you can get, right? It's a 2 by 2 matrix. Because I've done infinity by infinity matrices presumably at this point, but 2 by 2 is going to be very easy, right? It's fairly straightforward. So once we do the matrix algebra, we'll reinterpret what that means in the context of the original system. That's the plan. So to do that, let's get the eigenvalues. This will give you lambda square minus a plus d, lambda plus ad minus bc equals 0. This is a characteristic equation, and a plus d is the trace of the matrix, right? Trace of A, which I'm going to call tau, and this of course is the determinant of A, which we are going to call delta. Okay, so you have a characteristic equation that looks like minus tau times lambda plus delta. Delta is AD minus BC, yeah. Okay, so this is the equation we need to solve to get the eigenvalues. Of course, this is a fairly trivial equation to solve. Probably solve it in your sleep. And the solution looks like this, right? Quadratic equation. Tau square minus 4 delta by 2, yeah. Okay. Now let's step back for a minute and think about what this guy is doing. Okay, for simplicity, let's assume that the eigenvalues are real. Okay, they're not to be positive, negative, they're just real. For a start, let's assume the eigenvalues are real. If the eigenvalues are real, let's look at that case. That's the simplest case to interpret physically. So lambda 1 and lambda 2 are both real, and of course you know from solving quadratic equations that if one becomes complex, the other is complex conjugate, because imaginary part plus or minus, right? So if one becomes complex, the other is complex, it's complex conjugate. So they have to be in pair, they have to be either both real or both complex. So let's take the first case. Okay, if this happens, then what does that mean? That means that you can now find two real eigenvectors Okay, let's call them V1, V2. And if you look at the matrix A in this basis, so matrix A in this basis, it's going to look like this. Okay, that's what you mean by eigenvalues in the decomposition, right? I guess you guys have probably seen this 100 times before in the first part of the course at least. So if you represent the equivalent operator A, right, for which the matrix remember this matrix that we had A, B, C, D was actually, so the A, this was with respect to y1, y2, right? So your one axis is y1 hat, the other axis is y2 hat. They're mutually perpendicular, orthogonal to each other, right? That's how we drew the plane. So in this coordinate system, in this basis, your matrix looks like this. In this basis, the matrix will look like this because it's diagonalized, right? Because why is that? Well, because if you take A times acting on V1, you'll get lambda 1 V1. That's an eigenvalue problem. You've just solved that. V1 is the eigenvector corresponding to lambda 1. And similarly, A times V2 equals lambda 2 times V2. Okay, so in this basis, the matrix looks like this. That's an important point to remember. Okay. So now we can start interpreting what the consequence of this is. Now remember, V1 and V2 are two vectors, right? They're two-dimensional vectors. Just like y1 hat was z1 comma 0, y2 hat was 0 comma 1. This is like two components, right? So 2D or two component vectors, v1 and v2, because the matrix is 2 by 2. Since y1 hat and y2 hat form a basis for the phase space, remember the axis y1 hat, like you can think of it as I hat and j hat, if that helps. Since they form a basis, you can write v1 and v2 in terms of them. Okay, so you can write v1 equals some matrix, let me call it b1 times y1 bar. Okay, let me call it b1 y1 bar plus, let me call it b2 y2 bar. b11, let's do it like this. Okay, and then v2 bar will be b2 and y1 bar plus b22. Okay, in general v1 v2 are a linear combination of y1 and y2. So you will get another matrix B now that relates these, which has these entries b11, b12, b21, b22, and this matrix will be well behaved because the eigenvalues are well behaved. Presumably they are not dubious eigenvalues, they are not repeated eigenvectors and stuff. So we'll assume the good stuff, okay, and then we'll continue. So this matrix will be invertible. So you can write y1, y2 in terms of v1 and v2. So you can take the original differential equation. Why am I doing all this tamasha, right? Is this a reason I should be doing all this stuff? So you can take the original differential equation, which had dy1 by dt, dy2 by dt, and then cast it in the form of in the basis of v1 bar comma v2 bar. Okay, in the basis y1 bar comma y2 bar, this guy will be y1 comma 0, y2 0 comma y2, right? So in the y1 bar y2 bar basis, what we're actually writing here is the y1 hat. That's what this guy is, and we're looking at d by dt of this guy, and this guy is like d by dt of y2 hat, right? So 0 comma y2, this is y1 comma 0 in this y1 y2 basis. So I do a linear combination whatever, and then I move stuff to this basis v1 bar v2 bar, not the horizontal x and y that I had, y1 y2 that I had, but in some other oblique direction. This could be arbitrary, right? I mean, it could be something like this. Maybe this is going through the origin. Maybe this is my v1 bar. Maybe this is my v2 bar. They don't have to be perpendicular, right, unless the matrix has some properties, but they're certainly linearly independent. So any vector like this, I can either break it into y1 and y2 components, or I can break it into the v1 and v2 components. Doesn't matter. Okay, if I do that, and if I look at a trajectory in this basis as opposed to this basis, then the right hand side of the original equation, which is what I had here, with this, the right hand side of that, let me call the components of this along this as I don't want to use the same letter. Let me call this alpha 1 and alpha 2. Okay, so any vector I start here, this is, let's say this is my starting point, and the trajectory is actually going like this. So far I've been using this coordinate system to describe the trajectory. It's going around whatever. Now if I use this coordinate system, oblique coordinates, they are not orthogonal, but I can still use it. If I use this coordinate system, okay, then I'm going to get alpha 1, alpha 2 as the components along each of these, and then I will get d alpha 1 by dt and d alpha 2 by dt. That will be the parametric equation of that curve, the trajectory curve. But what will that be? Now this right hand side matrix is diagonal, remember, in this representation, in this coordinate system. Okay. So what this means is that this matrix will give you this and this. Okay, which means that the components referred to V1, V2 coordinate system are completely decoupled and the system becomes two 1D uncoupled linear differential equations. Exactly like we did that example, the first example where you had a diagonal system. Okay, so system becomes decoupled. So the moment you have lambda 1, lambda 2 real, okay, that means you can find in principle two directions, linearly independent directions, V1, V2, in which the differential equation will become decoupled. So this is what, okay, why do you want to do this? It's good because it now allows us to solve these two equations independently. Okay, that tells us that the component along alpha 1, the component alpha 1 along the V1 direction, the component alpha 2 along the V2 direction are either growing or decaying independently depending on the sign of lambda 1, lambda 2. Okay, so this becomes now analogous to 1D systems, decoupled. So you can solve them independently. So you can do the same thing we did last time with that. You remember this, we had alpha 0, 0, minus 1. We can do the same thing that we did over there. Same ideas apply here. Only thing is now trajectories will either become, origin is still the fixed point, so trajectories will either come like this if it's stable fixed point, or if it's a saddle, they'll be asymptotic to V1 or V2. Okay, we'll see how that is in a minute. You can basically do the same ideas. What did we have when we did, okay, when we did this alpha 0, 0, minus 1, we said when alpha was less than 0, it was stable, right? Why was it stable? Because, okay, one was decaying, anyway decaying because it was negative, and the other also decayed if alpha was negative, so it was stable. All trajectories, two components decayed. Same thing will happen here, okay? So if lambda 1 and lambda 2, remember both are real, are both negative, then you have a stable fixed point at the origin. Okay, if both are negative, because both components will eventually decay towards the origin. Both will be like e to the power of minus lambda 1 t, e to the power of lambda 2 t. Okay. If lambda 1, lambda 2 are both positive, then it's unstable because both are going to go e to the power of plus lambda whatever t. So the fixed point is unstable. So this we've figured out so far. Okay, so this is kind of easy to do. Okay, what happens? Okay, there's only two possibilities I've enumerated. One, both are negative, one, both are positive. What if one is positive, one is negative? So that means the product between the two is less than 0. Okay. If the product between the two is less than 0, that means in one direction, let's say if lambda 1 is less than 0, in one direction the component will decay towards the origin, in the other direction it will grow. So it's a saddle. Okay. So we have stable fixed points, unstable fixed points and saddles all appearing when both lambda 1 and lambda 2 are real, when the eigenvalues of the A matrix are real. Okay, let's write this down. Actually, before we write this one, let's sort of generalize this. These two cases, when lambda 1, lambda 2 is both negative or both positive, you can write it alternatively as this corresponds to the trace less than 0 and the determinant positive. Remember, tau is the trace and of the matrix A and lambda is the determinant, and in terms of the eigenvalues, this is just lambda 1 plus lambda 2 and this is just lambda 1 lambda 2. So if both are negative, that means the product lambda 1 lambda 2 is positive, so determinant is positive, but the sum is negative since both are negative, and so tau is less than 0. Okay. what happens here in this case? Now the determinant is again positive because they are the same sign, and the trace is also positive because both of them are positive. You add them up, you get a positive number. Okay. What happens here? This is a little bit more interesting. Not this, sorry, this. Now they are of the opposite sign, so the product is less than 0. So obviously delta is negative. There's something else that you want to keep in mind, which is that their sum could be either positive or negative. Depending on if the negative one is larger in magnitude than the positive one, then the total will be negative, and vice versa, right? So you can have tau either greater than 0, or you can have delta less than 0 and tau less than 0. Delta is always less than 0 because they have to have opposite signs, and the product is negative. Okay, but when does all of this? So you have 1, 2, 3, 4 cases depending on delta and tau. When will each of these 4 cases occur? They will occur only when the lambdas are positive. And remember what lambda was. Lambda 1, 2 was tau plus or minus square root of tau square minus 4 delta by 2. And this is real only when tau square is greater than 4 delta. Okay, so it's important. So all this entire scheme applies only when tau square is greater than 4 delta. Okay. Okay, so how can we try and represent these solutions? Okay, now obviously you can look at lambdas, positives, negatives, when is it moving, when is it crossing the real axis and so on. It's one way of course, but the simpler way to enumerate all of these possibilities is to draw what is called a tau delta diagram. Okay, this is a different diagram to what we have drawn so far, and there is no analog of this in the 1D system. Here, because we have two numbers, tau and delta, we have to deal with both of them. The 1D we only had one, so we didn't have to worry. We do the following. So let's have tau on the horizontal axis, tau on the vertical axis, and delta on the horizontal axis, and we'll try to represent regions in this tau delta plane, which correspond to stable fixed points, unstable fixed points, saddles, and blah blah blah. Okay. How do we do that? Well, first thing we need to do is we have enumerated stuff for tau square greater than 4 delta. So we'll draw this parabola. So let's draw tau square equals 4 delta first. Okay. So tau square equal to 4 delta, tau is square root of plus 1, delta is positive, so you will get a curve that looks like this and like this. So this is tau square equals 4 delta. So all the stuff we have done here, this entire thing here, is all outside this, because tau is greater than 4 delta outside this, right? So everything is outside this, not even on it, it's outside. Okay, so let's enumerate them out. So first, when tau is less than 0, delta is positive. Tau less than 0, delta positive is this area, but still outside the parabola is this area. So this guy is 1. So this guy is 1. Delta positive, which is on the right side of this axis. Tau negative, this is tau negative, but again outside this because we need a real root. So this entire area is 1, which is a stable fixed point. So the origin, if the matrix A were such that tau and delta fell here, then the origin is stable. Okay. Next, this guy, unstable guy, stable person. Where does this fall? Again, delta is positive, you have to be on the right hand side. Eigenvalue is real, so you have to be outside, either this side or this side. This side is 1. This is now tau positive, delta positive, it has to be this zone. So this, until the delta equals 0 axis, this is all unstable fixed points. Okay. The next is this, of course, this is 3. Now there are two possibilities. Let's call this 3A and 3B. and basically you need delta negative for both, so you're on the left hand side, and it doesn't matter if tau is positive or negative, it will always be a saddle. So this entire section will be 3a 3b. Okay, 3a will be tau positive, this will be 3a, this will be 3b. Okay, this is 3a, this is 3b, but they're all saddles. Okay, saddles. Okay, so that enumerates all that we've done. We've left out some, very strange characters in this diagram so far. First of all, okay, we haven't come to anything that is inside. We'll come to that in a minute. But we've left out the cases when delta is 0. So delta is 0 is the tau axis, this axis. And what happens when delta is 0? So let's look quickly at that. This is all done, so I can get rid of this. So if you have delta, I'll just look at that quickly and then we'll go to the complex case. So if delta is 0, that means either 1 of lambda, not both. I mean, if both are 0, the right hand side is kind of trivial and the whole differential equation is pointless, right? At least one of them is 0 makes it a little bit more interesting. And remember what happened here when we had that alpha minus 1 example. When you have this, that means that the d alpha 1 by dt, let's pick this guy. Okay, this is analogous to this. This is 0, is non-zero, is equal to some stuff, right? Lambda 2 times alpha, whatever. So the component, if you remember this figure again, the component, if this was v1, v2, the component along this was unchanged. So stuff that had a component along this will remain unchanged, this component. The other one will decay off to 0. Okay, so you will have things decaying. You will have one of the components decaying off to 0. So if this is unchanged, then it will come and fall like this. Just like if you remember the alpha case, when you had alpha equal to 0, stuff was just decaying out like this. So we call these non-isolated fixed points, if you remember. So all along this line, you will have non-isolated fixed points. It almost never happens in practice, but it's sort of a pathological case to be aware of, so that you know when it turns up. It's also important from another reason, from a point of view of bifurcations in 2D systems, but maybe I'll mention that at the end. Okay, good. So now we have we've worked out all the real case. What happens when tau square is less than or equal to 4 lambda? Okay. Now the lambda 1, lambda 2 are complex, and remember what lambda 1, lambda 2 were. Is this. Now, even though lambda 1, lambda 2 are complex, obviously the tau and delta are still real because the matrix is real. Of course, you can always add the diagonal elements, calculate AD minus BC, you will still have a real number, 2 real numbers. So you will still have something falling here, but now it will fall within this zone that we didn't talk about earlier. Okay. So what do we do here? This means that there are no real eigenvectors. Okay, if you have something that has complex eigenvalues, you can't get real directions in which to resolve the system and decouple the first order ODE, the two-dimensional first order ODE into two one-dimensional first order ODEs. You can't do it. You can't decouple them. Okay, because there are no real eigenvectors. Okay. So what does it mean if you don't have two real eigenvectors? Well, that means that there is no direction in that space, in the 2D space, that is invariant. Okay? If you remember again, the V1, V2 that we had drawn, these are invariant directions, right? You can think of this right hand side matrix, this A, as an operator. You can think of it as an operator that takes a vector and gives you another vector. It's a linear operator, right? You've seen linear operators in the first part of this course, so you should be able to appreciate what that means. It takes a vector and gives you a vector. What does it do? Well, it takes a vector y1, y2 and it gives you the rate of change of that vector. That you can think of it like that. Okay? If it acted on vectors in this direction, these are invariant directions, v1, v2, it will give you another vector that's in the same direction as v1, v2. That's what it was doing, right? That's the whole basis for the alpha 1, alpha 2, whatever we worked out. It was the fact that the vector, any vector that was here, stayed in this direction. It, got stretched or it got shrunk, depending on whether the lambda 1 was positive or negative, but it's always in that direction. So these are invariant directions for this operator. The matrix thought of as an operator. They're invariant directions, right? So if you give this operator a vector in that direction, then it's going to be always in that direction. And those two directions are properties of that operator, properties of the matrix, because the eigenvectors of the matrix, right? But now there are no invariant directions. If you can't decouple, which means if you can't get two real eigenvectors, then there are no invariant directions, which means there is no direction on the plane. Again, this plane is y1, y2 plane. There is no direction in this plane that will remain, where a vector, if you start in that direction, will remain in that direction. There is none. All directions will start getting shifted. Okay? So there are no invariant directions. Okay? And this is analogous to, for example, if you look at the rotation matrix, or your usual rotation matrix in 2D, probably seen this before. It has things like this. You can have plus or minus, different places depending on the direction which you are rotating. 2D rotation matrix. This will also not give you real eigenvectors. Why is that? If you apply this R to any vector, it will rotate it by an angle theta. There is no vector in the plane to which if you apply R, you will get the same direction back. It's always going to rotate it. Okay, so the rotation matrix is a situation that is an example of this, that has no invariant directions. And this is exactly what happens when you have complex eigenvalues. In rotation matrix also you can work out the eigenvalues, you will get complex numbers. You will get cos theta plus I sin theta and cos theta minus I sin theta, e power I theta. Okay. So the situation is analogous. So you can, wherever you start, you will get rotated, you will get moved out. So you expect all these rotation type trajectories and spiral type trajectories to turn up exactly over here, and that's what happens. Okay. When tau is 0 for this case, when you have this and you have tau 0, remember delta is positive here, delta negative is taken care of, right? We have had saddles, we figured that out. When tau is 0, that means the two eigenvalues are completely perfectly imaginary, and that means the matrix is something like this, some stuff 0, some other stuff and 0, something like this. Okay, and this we saw corresponds to a center. Okay, this corresponds to a center. So everything here on this line corresponds to a center. I think I don't know if I defined a center. A center was basically where you had these cycles that were oscillating around depending on where you started. If you started here, you went this cycle. If you started here, you went on this cycle, and so on. So the origin, when you have a situation like this, was a center. This was the example we had, right? This is 0, 1, q naught. So this origin now is a center. Okay. So when you have tau equals 0 but delta positive, you will have a center like that. So these will all be Lyapunov stable but not absolutely stable, all of them, every point here. Okay. Good. Now what happens? So we have taken care of this entire zone. We have taken care of, okay, we'll come to the parabola itself later. Tau square equals 4 delta. Okay, this means that the eigenvalues are equal and real. That square root thing is 0. So this is also either unstable or stable, but the points will all come towards the origin along lines. I think we worked that out in that alpha example again, right? So that parabola also is taken care of. The only regions now are this region above this axis and below the parabola, and this region which is below this axis and above the parabola. Okay. So what about those? So those also are interesting. I'll give you an example in the next assignment where you will work this out explicitly. But right now we can figure out what they look like. If you have tau positive, okay, delta is of course positive, you're within the parabola on the right hand side. If you have tau positive, that means lambda 1 plus lambda 2 is positive. Okay. And if lambda 1 and lambda 2 are complex conjugate, then the real part of lambda 1 is the same as the real part of lambda 2. Okay. So the real part of lambda 1 and lambda 2 are both positive, because if the sum of two things is 2 times real part of lambda 1 lambda 2, and so this is also positive. If the real part of lambda 1 is the real part of lambda 2 and they are both greater than 0, that means that the origin is an unstable spiral. Okay, I'll give you an example in a minute so that you can work this out, but then stick along for a little while. And the converse, if you have tau less than 0, then the converse of this holds, and so now the origin 0, 0 is a stable spiral. And it turns out that if you have the real part of the lambda positive negative, then you will either keep increasing that y out if it's positive, or if it's negative, keep reducing the y. Okay, so you will get positive. I'll work out an example for this now to show you how this works. Okay, so let's do that. So here you will get an unstable spiral, and here you will get a stable spiral. Okay, good. So let's work out an example. So let's say I have this equation, d square y by dt square plus p0 dy by dt plus q0 y equals 0. Let me change this to omega square, and this is 2 xi omega n square 2 xi omega. So this is a spring mass damper system. If you have a system like this, you have a damper, you have a spring, and then you pull and you let go. So it's free oscillation of the spring mass damper system. Okay, and this you are measuring y from some datum where the spring is unstretched. Okay, so if you do this, you can cast this system just like we did before. So you have y dy by dt is y1, or let's call it y2, y is equal to y1, and then you have dy1 by dt is dy2 by dt is minus 2, that is this guy, d by dt of dy by dt, dy by dt is y2 minus 2 xi omega n, and of course remember xi is greater than 0, omega n is greater than 0. Okay, minus this times y1 minus omega n square times y2. Oh, sorry, y2 y1. Doesn't come diagonal. So now the matrix A for this case is 0 1 minus 2 xi omega n y2. Sorry, so this should be minus omega n square minus 2 xi omega n. Okay. So that is A. So we can do the same thing. Okay, now firstly you can solve this problem. This is a standard linear constant coefficient second order ODE. So you put the usual stuff. You put try y equals e to the power of RT, and then you can solve this problem. You will get r square plus 2 xi lambda and whatever r, and you can solve this. Okay, that's doable. So you know the solution to this. So solution to this looks like some e to the power of minus some stuff times t times sine of some other stuff times t. Okay, these are constants. It will be square root of omega n and xi and so on, but I am not going to worry about them. Okay, so some constant e to the power of some constant times t. So that is for y1. Okay, and some other constants in front. Again, these constants don't matter. So I am going to put a tilde sign here. And similarly for y2, same t but with a cosine of some stuff times t. Plus, if you take a derivative of this, you will get some other constant times e to the power of minus something times t sine of something times t, right? Same constant comes here, but okay, you will have two terms when you take a derivative. Okay, so these are all constants. Again, I'm not going to worry about the constants. But what does this trajectory look like? If xi is positive, zeta, okay, zeta, let's call this zeta. If zeta is positive, then this constant are all positive. You can work this out. I'm going to give this as an assignment. You can work it out. I'm not going to do it here. Right, it's very straightforward. So then the zeta, if it's positive, then you have a positive e to the power of minus positive number times t, and so the trajectory is going to decay, okay, away to 0. And it's not just going to decay in a line, but it's going to decay like a spiral. Okay, so it's going to start from here. It's not going to come like this, like the stable fixed point, but it's going to come like this, and eventually come to the origin. Okay. What are the lambdas here? So the lambda, well, let's get the tau. So the tau is this the trace, it's minus 2 xi omega n, and this is negative. So you have negative here. This is a stable spiral. Okay. If you had xi positive, which means the damping was not impeding the motion but actually aggravating it, then the system would become unstable. You can work that out as well. You will get this coefficient will now become positive, so you will get e to the power of some positive times t. So that amplitude will start growing with t. Okay, you can again work that out if xi was positive. So you will not, if you start from here, you will not get a spiral coming to the origin, but you will get something that goes out. So the origin will be an unstable spiral. Okay, and that's again what this predicts. If psi was negative, then this is what will happen. Okay. Notice now that this omega n square is there, and omega n square presumably means that it's a positive number because omega n is real. So the determinant is now this, which is 0, minus this, which is positive. So determinant is positive, so you're on the right hand side. So we checked out. Okay. So that finishes these two parts, and then we're complete. You know, this tau delta diagram is complete. So we have all the parts that we need for this tau delta diagram. Okay. So what I will do next is we will see how to apply this for a nonlinear problem. So far all of this is a linear system. We have A, we have A, B, C, D entries of A, and then we have seen, depending on the eigenvalues of that matrix, eigenvectors and so on, we have said something about what the behavior at the origin is. Remember, the origin is the only fixed point. It's a linear system, origin is the only fixed point. Okay. So we've said all this about the linear system, but now what about the whole premise of setting all this stuff up is to talk about nonlinear systems. Okay, now let's say you have a situation like this. Like this, two equations, f1 and f2 are arbitrary nonlinear functions. Again, autonomous for now, we won't worry about non-autonomous, but f1, f2 are arbitrary functions, non-linear functions of y1 and y2. So it's a function of two variables. Now remember what we did when we had a similar system in 1D. We did linearization. So we found the fixed points. Remember the three-step process. We find fixed points, then we linearized about fixed points by doing Taylor series expansion, and then we find stability, determine stability of each fixed point. Right? That's what we did. We do the same procedure here. The only, when we started, I think I mentioned this again, doing the same procedure. The only problem we had then was we didn't know what to do with this. We had a matrix as opposed to a single value. Now we know what to do with this, because if you give me a matrix of a linear system, right, we can look at tau, we can look at delta, and then go back to the parabola and look at is it stable, unstable, whatever, usual stuff. Okay, so let's do that. So first let's find the fixed points. So the fixed points are y1 star, y2 star are fixed points. So you have to solve two simultaneous nonlinear equations. Okay, two simultaneous nonlinear equations, and you will get values, maybe multiple values of y1 star, y2 star. So you might have multiple fixed points, okay, not just one. And so that's the first step. So first step is done. What about the second step? The second step is to linearize. So this process, linearization process, is identical to what we did with the first order system. Only now we have two variables to linearize in, not just y, but y1 and y2. The procedure is the same. You do Taylor series expansion. Now you have to do Taylor series for multiple variables. So you assume that eta 1 of t is y1 of t minus y1 star, eta 2 of t is y2 of t minus y2 star. Okay, and you have f1 of, so okay, then you have dy1 by dt is the same as d eta 1 by dt, and dy2 by dt is the same as d eta 2 by dt, because their y2, y1, y2 are constants, y1 star, y2 star are constants, fixed point coordinates. So the linearization, remember, has to be done about a fixed point. So if you have multiple solutions to these two equations, then you have to linearize about each of them to find the stability of that particular fixed point. If I use this, I can go back to f, which is f of y1 comma y2. f1 is, now y1 is eta of t plus y1 star, and y2 of t is y2 star plus eta 2 of t, and again I can do Taylor series expansion of this. So I'll get this is equal to f1 of y1 star comma y2 star plus dou f1 by dou y1 of this eta 1 of t plus dou f2 y2. This is evaluated at y1 star, y2 star. Of course, this one also y1 star, y2 star times eta 2 of t plus higher order terms. Yeah, just simple Taylor series expansion. Of course, this is 0 because y1 by 2, y1 star, y2 star is a fixed point. So you will be left with this as the highest order term, lowest order term, sorry, the leading order term. Okay. Similarly, you can do for f2 of y1, y2. Same procedure, that will now be equal to dou f2 by dou y1 times eta 1 plus dou f2 by dou y2. Again, these derivatives are evaluated at y1 star, y2 star, eta 2 plus blah blah blah. Okay. So you can take this linear system, do the same scheme, and found the fixed points. We can linearize the system about some fixed point, one of the fixed points. You linearize the system and you can write d eta 1 by dt is equal to a eta 1 plus b eta 2 d eta 2 by dt C eta 1 plus D eta 2. Okay, and then this, of course, A, this is, I'm calling this A, this is B, this is C, and this is D. Okay, so now the matrix A, which is A, B, C, D, now basically has dou F1 by dou X, sorry, dou Y1, dou F1 by dou Y2, dou F2 by dou Y1. Okay, this is the matrix, also called a Jacobian matrix, you can call it J if you want. Okay, but remember this matrix is a constant because it's evaluated exactly at the values y equals y1 star and y2 equals y2 star. Okay, so it's a constant matrix. Now you have the constant matrix, you can do the same thing that we did there and you can find the stability. So we found this stability just like we did from the tau delta diagram. So you get the trace of this matrix, get the determinant of the matrix, see where it falls in that tau delta diagram that we had there, and then it will tell you if this particular fixed point y1 star, y2 star is stable, unstable, spiral, saddle, center, whatever. Okay. Okay, good. So in principle, if somebody were to give you a nonlinear equation, I will do that in the assignment. I will give you one very famous nonlinear equation to work out, which a lot of people have recently had a lot of interest in. If you do the linearization, you can find the fixed points of that system, and you can find if the fixed points are stable, non-stable, unstable, whatever, right? And the usual stuff. Okay, so this procedure is analogous to what we did for the 1D case. Now I'll just talk briefly about bifurcations. Again, I will leave this idea out for the 2D systems because it can be a little bit complicated. This is the first course in nonlinear. In ODEs, you've probably never seen nonlinear ODEs being worked out before. So I will say a few things about bifurcations and then we'll stop here for the nonlinear part and then we'll move on to series solutions next time. Okay, so this will essentially end our discussion of the qualitative stuff that you can do with nonlinear second order systems. Okay, and the reason we had to build up all this stuff for the linear second order system, even though we know how to solve it, is so that we could come and do the linearization and do this scheme for the nonlinear case. Okay, that's why we had to spend so much time to do this. Okay, bifurcations. Okay, now in 2D, 1D, remember we had the usual. We had this lambda and you change lambda and there's a qualitative change. Qualitative change in behavior. Okay, in 2D, the same stuff happens. Okay, same as what happens here, but in addition, you have more complexity. What complexities can you have? Well, now you have centers. So the fixed point can be, so if you had just two fixed points with both stable or unstable, then you can have saddle node bifurcation, you can have pitchfork if you have 3, you can have transcritical if you have 2 and things like that. The usual stuff that we discussed for the 1D case applies here as well. There are, you can make up examples that do this. But in addition, now you have these centers and you have these spirals. Okay, so you can now have bifurcations where centers become spirals. Spirals go from stable to unstable and things like that. Okay, which we haven't spoken about. I mean, it's possible. You can easily imagine this type of thing happening. You could also have fixed points becoming spirals and vice versa. That's a possibility. You could have fixed points becoming saddles like you had before. That's also a possibility. And so you can sit down and basically work out the same type of algebra that we did for 1D systems, even though we won't do it for the 2D case. Okay, I'm just telling you that it can be done. Okay, so that should give you an idea of how you can approach a 2D nonlinear system in general, or a general nonlinear second order differential equation, autonomous, and how you can use some of these techniques to analyze first fixed points and the behavior. Now, this of course is same as what we did for the 1D case. It gives you information about what happens as t goes to infinity. So does the trajectory grow? Does it blow up? Does it go towards the fixed point? Does it keep oscillating around it, and so on? So those are things you can answer with an analysis like this. Now there is one word of warning, which I'm going to call a caveat. In many cases, especially in 2D systems, in 1D not so much, in 2D system linearization can fail. Okay, so you have to be careful if you ever start working in this area, doing instability, studying instabilities or doing perturbation analysis and so on. You have to be aware of this fact that linearization can fail, and it fails most dramatically in what are called limit cycles. Okay, limit cycles are isolated closed trajectories. I haven't discussed any of that. We won't talk about it because it needs a little bit more time to develop in completeness. So you can have these limit cycles which are not like your usual trajectories. Usual trajectories, if I change, there's one more. If I start the initial condition here, there's one trajectory. If I start it here, there's one trajectory, and so on. This is a usual center, right? Origin is the center. But you can also have what are called limit cycles in 2D, which don't appear obviously in 1D. Okay, and these limit cycles are very peculiar because if you start exactly on the limit cycle, you will keep going around it. If you start close to the limit cycle, remember what happened here. If I started close to this closed trajectory, I was going in my own closed trajectory. But if I start close to a limit cycle, I will go and eventually either reach the limit cycle, or I will go away from the limit cycle, or I will go to the origin. So you can have these types of behavior in 2D, which is not there. The linearization will not cover this. You cannot get this type of thing by doing linearization. Okay. There is a way to work on systems like this. You can convert to polar coordinates and look at trajectories deviating from the limit cycle trajectory, from a potential limit cycle trajectory. There are perturbation techniques that you can use to detect limit cycles, to look for periodic solutions of the ODE and use that to identify the presence of limit cycles. There are geometric methods. There's something called the Poincaré-Bendixson theorem that tells you how you can identify limit cycles by looking at what trajectories far away are doing and what trajectories close by to the origin are doing. Okay, and so there are some of these techniques that you have to use. They're a little bit more specialized. It depends on what type of nonlinear equation you're looking at and what you're interested in. So depending on that, you'll have to pick one of these slightly more specialized techniques. But as far as we're concerned, taking a general nonlinear system, finding the fixed points, and doing linearization above the fixed point and classifying the fixed point as being one of the many we enumerated in the tau delta diagram should be sufficient, okay, for our purposes. So with that, I'll stop this discussion of nonlinear systems. We will next move on to a discussion of series solutions. There are only 2 sessions left. The first one will be on series solutions. I'll give an assignment on all of this stuff on the second order, whatever we've done in the second order system so far, and we'll look at series solutions. I'll show you how some important ODEs come up from PDEs, and then I'll show you how you can use series solutions to obtain a solution for these PDEs. So that will sort of complete the loop. We started from PDEs, we said ODEs are important, and now we're going back to PDEs. That will complete the loop a little bit. And then the final session, I'll talk a little bit about numerical schemes. Okay, so that if you ever want to implement a numerical scheme for, let's say, some type of nonlinear ODE, you should be able to do that. You should be able to say something sort of semi-literate about how much error you're going to have. Of course, now it's very convenient. There are lots of packages available for doing numerical integration for initial value problems. But it's always important to know where these come from so that you have a feel for how much error you're introducing, what the convergence rate is, and things like that. I'll give some brief idea to that. And then we will wrap up this entire discussion of differential equations with that. Okay, so we'll have 2 more sessions.